All right, so some issues with k-means squares, okay? So one is that initial parameters really matter. Basically, I made a little note, hill climbing. Have we talked about the term hill climbing, or does that sound familiar at all? So if you remember back to gradient descent, let's see, actually, I'm not sure if we talked about this gradient descent, but one thing with gradient descent is that, remember it's trying to find like the minimum over like this kind of like hill. Well, the problem is if you have this nice little, you know, this nice little minimum right here, and then all of a sudden this minimum goes down like even deeper, like this. The problem is that the ball, like I mentioned, like there's someone like, I mentioned about like bird boxing down like the hill, like blindfolded, trying to go down this hill. You find the bottom here, and you try going uphill. It's like, oh, that's going uphill. I'm just going to stay nice here in this, what they call a local minimum. Essentially, that means is like it doesn't want to really try to go up this little hill to find even better minimum. Remember, it wants that minimum. So one problem is that k-means is really like initial parameters where you start off at really matters. Where if you imagine if you started like right here climbing, so there's my little person on gradient descent, this is kind of analogous to it, is that if they start going left, they would definitely find that local minimum. But if they started over here, you can see that this is not going to, they're likely not going to find this actual minimum. They're just going to find this local minimum here. Okay. So what are some ways we can prevent, since initial parameters matter a lot, what could we do to kind of like try to circumvent that? Anyone got an idea? So one, how do we initially find our first centroids? What did I show you guys we do?
Random and you choosing.
Yeah, so random me choosing, right? So you can probably guess is that if I choose, for example, always like a certain spot, that would not be good. So randomly, it's probably a pretty good choice in this case, right? And that would decide where the centroids are. Except initial parameters still matter. So by chance, we still might not find the best space, right? So what could we do if these initial parameters really matter? What could we do on k-means to prevent this, like finding this local minimum versus the global minimum? How would you solve this problem if all you can do is walk down the hill? So one thing you could do is instead of having one person start off at one spot, you can have multiple people. One person start here, one person start over here, one person start over here, one person start over here. You randomly try different initial parameters. You try to start off at different places. And that's essentially what the biggest fix for this is, initial parameters. You're like, hey, let's just randomize it and then run it again. Okay, so that's kind of like the idea there. The second issue with here is clusters are not always what we expect, and this is because of the local minimum. So I think I kind of showed it right here perfectly by accident, but let me go ahead and restart. I'm going to choose it just to kind of put it in a situation. So I think one of the things where it was like right here, and then I put a third centroid right here. The problem is, so this is let's pretend this is randomly just how it assigned, right? Which I actually did at one point. But if I do this now, you'll see that this isn't going to really change that much. It didn't find the proper point. So this is finding a local minimum where really we want this green part just to move a little bit off to the right, or this blue part move off to a little bit of the right, and that would fix everything, right? So it tends to try to find these local minimums. So again, what we can do is just basically restart it, do it again, go through it, and then, go from there. And then hopefully as we kind of proceed forward, it'd figure this out, right? And then hopefully on average, we'll be able to figure out what the actual clusters are. But you can kind of imagine that's not super efficient, right? But we could technically do it that way, okay? So just to kind of show you like this local minimum, like how this is such a huge issue, I'm gonna show you a couple examples. So pretend we have these three different clusters, right? And so imagine what I wanna do is there a way, and so we're purposely trying to break the machine essentially. Is there a way for us to start off the three different centroids so we find a local minimum where there are only two groups versus actually finding three different groups? I kind of showed it to you guys, kind of cheated. So I'll kind of show you guys. So let's say I start off one right here. This is my first centroid. This is, I obviously use the same color for each of them. This is my second centroid, and this is my third centroid. As we saw, what's going to happen is that this is going to be classified as one group, and this is really going to be treated as essentially like one other group by itself with its two centroids. So you can see that here is that basically these are going to fight it out. It'll technically make it into three, but you can see how it's going to essentially make this one group right here and another group here. One thing you can do with k-means is say, hey, are these centroids really close together? And if they are, oh, that's really should be one group. So the problem is this is really going to identify as two different groups versus the actual three. And that's just out of pure chance. That makes sense? Okay, and that was kind of like what I showed with the example with the k-means over here, which if you look right here, I kind of want to just emphasize this point. That's why I was, no, choose Gaussian. So 1, 2, and then 1 right here. And you can see here, it's just never going to really improve. Like it's not really going to do anything different. Okay, so we can get this issue. It's not likely, but it can happen. Okay, and so let's see another example here is that if I have two groups like this group and this group, I'm going to argue is that, so I'm going to say there is a way to initialize the two centroids where instead of having a group like this and a group like this, we'll have two different groups, but they'll be split where some are going to be blue and some are going to be orange. And then the second group's going to be some blue, some orange. You got an idea what that would look like?
Would it be the points in the middle, one kind of near the top, one kind of near the bottom?
Yeah, so yeah, you got the right idea here. We'd have one like in the middle, they're both in the middle, but one kind of to the top, one kind of in the bottom like this, Andrew?
Yeah, or even further down, maybe.
Yeah, it could be even further down. Yeah, that's a good point. So we could have something like that looks like this, right? But the point is like if they're pretty much on this spot right here, they might basically say, well, these points are really close to it. So it's going to essentially going to end up being right here. And these points are really close to it. So it's going to say, okay, let's keep these ones over here. And so essentially we'll have two groups, but you can see they're mixed over. So it's not likely that they'll land so perfectly like where they're balanced out, but it's technically possible. And that's the stuff we have to worry about. It's like, it's not that, is it how likely is it? It's like, is this possible? This means like, these are the ways it can fail. Okay. Does that make sense to people? Okay, cool. All right. So you can already see like k-means can sometimes have some issues in there. So in summary, basically, k-means really relies on the distance to centers, like these lines. It's looking for circular data. Like I say circular, this is not great. I just say like blobular, I don't know, blob data. Okay, it's looking for clusters all together. When we see clusters that are kind of like all clustered, like really close together like this, it's going to do a better job doing that versus like these elongated parts. It's just going to have a hard time figuring these parts out. Okay, and also that k-means relies on having the right centers. If you don't have the right number of centers, it's definitely going to not perform very well. Okay, so this is where we can actually use different shaped clusters. If you guys remember back to maybe like mod 3, where we talked about data generation, we talked about how to make these different samples and stuff like concentric circles, moons, blobs, and stuff like that. This is kind of like a way to test our algorithms to make sure that how they're going to perform. So if we know our data for whatever reason has more kind of like this concentric kind of like look to it, then we don't want to use k-means for this because k-means is going to perform very, very poorly. Does that make sense? Yeah. Everyone understand like k-means cannot identify this. Like we'll never be able to identify this circle as one group. That makes sense. Since it's really looking for essentially these kind of like clustered kind of blobs together, as you can see right here. Okay. So this is where it comes to, okay, like, well, cool, here's k-means. Well, hey, there's a whole bunch of other algorithms, and that's where we can go next. So what we're going to do after this is what the curriculum talks about is hierarchical algorithms. So this is like Ward and agglomerative, I don't know, agglomerative. I cannot say these words. This is where like I just say agglo clustering. So you can see here is that this is what we're going to go into next. Okay.